Okay, awesome. I want to do kind of, this will be low level in terms of what we are working with, but not low level in terms of the concept. So I'll be building on what we've basically just heard on the topic of how do futures work, and just talk about how do we use them in embedded systems. So embedded systems, and I'm using this introduction slide time and again because everyone has different ideas of what is an embedded system. When I'm talking of those, that's like microcontrollers in the league of, say, a few hundred kilobytes of flash memory and maybe 100 kilobytes of RAM, quite possibly lower, even though the ones that are currently more popular are more on the higher side. They usually have one single chip, and they have peripherals on board for things such as toggling pins up and down, exchanging serial data, doing analog stuff, etc. They often also have network access, although in many cases more the low power networks, so say LoRaWAN, 802.15.4, which is powering Zigbee and 6LoWPAN, those things. Wi-Fi is present on some of those chips, but that's more for the bigger chips because it's just a rather complex protocol. The way we're programming on such devices is usually that things are bare metal, which means that, okay, well, that's interesting colors, but anyway. We have the machine's RAM here on your right side and the ROM on the left side. And the machine itself is basically the CPU that has all its registers, a process count, program counter, a stack pointer, and that is executing the program. Basically, starting at starting at address 0. It's like it's following a pointer there, but in the end, it's starting at address 0 and working off instructions. And every instruction increases the program count. It's like a regular program, no threads, no fancy stuff. The memory setup is usually such that there is some static memory, which is for global variables, for things that are initialized either as 0 or with data from the program. And there's a stack setup, and that is just growing and shrinking as the program execution continues. You might have a heap around, but in a sense, the heap is nothing more than a part of the static memory that is managed by something we call an allocator. You may or may not want to use them on an embedded system. So this is very simple and convenient. But the question is, how do you do different things at the same time? So for example, how do you both interface with a network and react to changes in the button? And the easiest solution is you don't. The easiest solution is you have just one big main loop, you loop through that, and when a button is pressed, you do something, and when something is trying to connect on the network, you accept the connection, you receive data, you send data back, say you're doing a web server whatsoever, and then you close the connection, and if someone presses the button in between, they're tough luck. Always depends on the use case. There are use cases where this is perfectly fine, and and this is easy because this just by the time you're accepting the socket, you're creating a connection. Your stack is you reallocate that here. Your stack is growing down. When you're done with it, your stack goes back up. Everything is fine. Everything is easy. There's one more thing that you can do, and that is something that you only really encounter when you're doing low-level programming, either on a bare metal microcontroller or building an operating system on larger hardware. That is interrupt handling. So as part of this whole startup routine, you usually set something like an interrupt, kind of different ways, but there's something like an interrupt vector set, and that is a series of callbacks. And at any time during processing, so no matter where your program counter is, where you're in your functions, an interrupt can fire, and then some other routine, this jumps over somewhere, executes some routine, possibly on the same stack, possibly on a different one, but kind of still growing around somewhere around here, executes some small piece of code, and then jumps back. So another way you can use it on, you can do concurrency on, or actually the first we're showing here, doing parallelism on embedded, is you just pack things into such events. So you're registering an interrupt handler, for example, for button pressed. Whenever a button pressed, you execute some code. This works fine for button presses. For more complex things, you usually have to do a state machine to advance those things, and that is also the kind of part of the third model of doing things in parallel in a microprocessor. That is, you have a main loop, and instead of at some event starting to go into a routine, you just store the state of that routine that you're doing, because you're dissecting the routine into a state machine manually. You have that state at the top always available, and then whenever some event comes in, for example, because you polled your device and it said, okay, yeah, there's an Ethernet frame pending, and then you look at it, and if the state machine is in that state, and if the event is a new connection, then you reject it, and if the state that is the event that is coming in is data, then you process it. But this gets messy really fast. So you can do this, and it makes sense in many cases. But it's hard to maintain. It's complicated, and like things. It's mainly hard to maintain, both at write time and at read time. So what do you do with your PC when you don't want to do things in parallel? PCs usually provide you with threads. And on a microcontroller, you can do that as well. That usually means that you're running some kind of real-time or embedded operating system. Those operating systems can do quite a few things, but the one that I'm interested in here is that they manage threads. So at startup time, or whenever you create those threads, you set aside some memory, which might really be kind of statically allocated memory, but still there's a portion of the memory that you allocate to a particular thread. And then the program counter gets set to a particular entry function. The microprocessor starts processing that function. And at any time, and that can really be any time, like in the middle of you're reading some variable, incrementing something, writing that back. At any time that the operating system permits, and that can be very that can really be anywhere in your code, some interrupt fires and changes the program counter, stores everything that is part of the machine state into a part of that thread, then restores that part from another thread and continues executing there. So really, your program can be interrupted at any time. And that is very convenient, because when you look at the code you're writing for such a scenario, that is just like the code as you had before, but with the extra benefit of not blocking. So, for example, if you have this network one thread running this network loop, while you're receiving data and the button is pressed, the operating system can just jump over to the other function and process that, because the button has just been pressed, and then come back. And it doesn't matter too much for that, whether that is like time-sliced multiplexing or whether that is event-driven or what's or not. Point is, one function gets left at the state where it was. Execution jumps over there and continues. So that would give us a lot of things already, but there are downsides to this. One downside is that task switching on the microcontrollers does need some time. That the tasks become easier with the more modern processors, but that also means that the more modern processors are becoming more complex to account for that, for easy switching. One important, and to me the most important problem, is that for each of the threads that you're having, you have to allocate a stack, and you have to know in advance how large that stack should be. So on a PC, it's easy. On a PC, you have a memory management unit. When the stack grows beyond some size, there are various mechanisms that just allocate more memory into there, and things continue. You have a few gigabytes to spare RAM anyway. Here we're talking about maybe 100 kilobytes of RAM, so not too much to work with, and no tools to reallocate that once a thread is becoming too large. Those sizes are also a bit difficult to predict. So there are tools that will tell you how large that the stack of a particular function would need to be. But those tools have a tendency to just report infinite, because there's some recursion and they can't see into that, or there is some function pointer interaction and they can't see which precise functions might be called there. So this can blow up quite easily. But it's very convenient, and it's done a lot of times. But there has to be a better way. And before I get to that, there's one more interesting aspect about this. That is the topic of synchronization. Whenever a data so most data structures are local to the threads. So, for example, the connection, which in this image before here, where was I? Yep, here in this model, we had the connection allocated basically at the start of our stack, because we did that at the start of the program. Here we do this in here, so that connection never leaves the thread. But other data structures might be shared. For example, if you want to report that counter that we're incrementing on the button press over the network, then both processes need to share some memory. And if the memory that is being shared there, or if the data that is being shared there is not sent or wrapped into something that is sent, for example, a pointer that is sent, it cannot be safely shared between the processes, because there might be one process that is just reading that variable, incrementing it, writing it back, and if two processes are doing that at the same time, they can't know when it is safe to just do that, because there is preemption. The program can be stopped at any point in time and continued later, and something else is working there. So for this model, you'll always need to go through something like atomics, like an arc, as we had avoided it in the web example before, because the web is single-threaded. So communication between those threads needs something that is sent, and that goes just the same for interrupts, because especially looking at the images, a thread isn't really something different from an interrupt is not really something different from a thread. So from Rust's point of view, everything is a thread if it can preempt some other code. And that is the real criterion for something to require send on its data. So whenever there's preemption, we'll have to take a bit more care with our data structures and use the possibly more expensive atomic operations compared to the cheap increment decrement operations that we can do otherwise, and that the compiler can elide in many cases. So let's look at another model, and that is the async model. That is the kind of main topic that I'm building towards here. When we are using an async executor on a microprocessor, we're usually running on a single processor. There are ones with a single CPU. There are ones with multiples, but not too relevant for this particular case. And they're usually also running just a single executor. So within that executor, we are allocating a few tasks, which are really just big enums generated by those very mechanisms that we've talked about earlier, where the async function is turned into an enum. And those most of the time, those sit there idly, and the stack is shrunk to whatever the main loop is. And only when the waker is called and some task has the chance of continuing, then that enum is polled, or that type is polled. We are running through whatever the synchronous code is that can make progress on this struct. That is building up our stack. That stack is growing back down as the function completes, and in the course of that, it updates that particular task's state. So looking at an example of what our code would look there, it really looks a lot like the threaded code, but all the points where we have a chance of relinquishing control over the CPU are annotated with that await. And when the future is built from that, the parts between the await are what is actual synchronous code, and that every await represents a state in which the task can be stored into that enum, or at least every await that is not optimized out because it's not really awaiting something. And this has the nice property that we know in advance a lot about our sizes. So everything that is a task can be up here, very similar to how the connections in the earlier example where we hand-rolled all our state machines were allocated at the start. Here also we have those tasks at the beginning of our memory, or in static memory. It doesn't kind of it lives throughout the execution of the program. And if two functions, and that is something that happens a lot of time, if two functions both have some requirements on using a lot of stack size, that stack size is in many cases just used between those await points. So whereas in the thread model, each of those threads would have needed some large chunk of stack space to account for example, cryptographic operations that just take some more memory. In this model, they can share this memory because they are not because the blocking because the synchronous operations are not running at the same time. Only when one of those is done with its synchronous operation, then the next gets its chance to run. So this allows programs to run with a lot less of with less memory requirement because they collaborate and don't rely on an operating system to rip away control of the CPU at any point in time. Yeah, there are more kind of some more advantages and disadvantages compared to a thread model. I mean, for example, this one advantage is that this works more portably more easily. So creating threads and using the primitives for communication between threads is usually something where you're depending on the platform. And yes, the standard library in Rust is abstracting that away for us. But the standard library is often not available in microprocessors because their world is just not shaped in a way that fits to the standard library very well. And the tools that we're using in the async world are a bit more suitable for reusing the same code, even though we're running in different environments, as long as they're all async. Yep, I think so. Yeah, main point is this works well. This can be used with a lot of tools. So that's where I'm going to tools and further reading. The primitives that we're using there, like futures, they're just already part of the core library. Many of the tools in the embedded world, network abstraction, hardware abstraction, are available. And by the way, slides are online and you'll have a QR code at the end. They provide asynchronous APIs. And different environment runners are available for the various platforms. So, for example, Embassy is the most popular, I think. Asynchronous. It's hard to tell what it is. I'd say framework, which just provides all the tools with which you can build an application. The Riot operating system, which is written in C, also implements many of the asynchronous. Also, basically, it uses the Embassy executor, but then also provides quite a large number of its facilities in an async fashion. And yeah, basically with that, especially those two, if you want to try it out, just take an off-the-shelf microcontroller and give it a try. I've linked to 2 blog posts on the topic that also inspired this talk. That talk a bit more about the various strategies of how asynchronous code can be executed. So there's a bit more to it than just having those tasks all on the top next to each other. So for example, you can make progress. You could set things up in such a way that when there's an interrupt firing, one of those tasks can make progress, which is great when you have tasks that you want to run at a higher priority. But it also comes with downsides, because then all of a sudden that task needs to be, the futures in the task need to be sent, because they are now sent between the thread that is the main task, or that is the main executor, and the thread that is represented by the interrupts. So there are trade-offs, and you can do different things depending on how you set up your system. But there are also easy tools available so that you can get started, and asynchronous Rust on embedded is, I think, no more scary than just regular development. Okay, with that, I think that, yeah, that is right on my 20 minutes. So thanks for your attention. Slides are online, you can see them there. I'll be around for questions now and later, so yep, thank you. Any questions now? Yes. So if you that is true for most asynchronous programming. If you start blocking somewhere in there, things take longer time. Sounds dangerous, but then again, when you look at how things work with threads and how many embedded operating systems implement things, more often than not, when there is something that really needs to be synchronous and can't be interrupted, they just start doing a critical section, disable interrupts, do their work, and those are just the same things that will starve your program. So yes, be a bit more careful in the thread model, but yeah, there are foot guns on both sides. Yes. Actually, there's like only there's only two ways really to get the thread to switch. Either the thread says, okay, yeah, well, like I'm done now, please pause me and start scheduling, or there needs to be an interrupt that does this because nothing else can. There is no magic thing that will. Threads are not magic. They don't just switch over. Some code needs to run, and if that code is not executed by what is currently running, it needs to be executed by an interrupt. Yes. Yeah. So just to repeat for the recording very briefly, how do I keep the code small? Yeah. um, pray? No. um, um, hmm? Yeah, don't write a lot of code is a good idea. Another is keep an eye, basically look at the output of nm dash dash demangle and look what is eating up your code. And when you see that something is monomorphized more than a few times, especially if it's large code, consider sending it through a dyne dispatch. Consider tweaking the inlining a bit, but especially on highly generic things, think about where monomorphization happens, and when you profile it and you see that this is there's too much, this is more code than I expect for this functionality, look at whether anything of that can be sent through, for example, through a function that will be identical for those. Yeah. Yeah. The, 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 um, so is there something else in there? I think the idea of the await adding something isn't quite capturing it. So when the compiler goes through this, it's not like this is staying as a big function and await something happens. It is more looking at all the local variables that are persisting through sections of that code and packing that basically all the locals that are living through await points are sent from the stack where locals usually live into that enum. And then it just becomes one of those poll and then it becomes just an implementation of those poll functions that we've had earlier that has a big match on where am I in that enum and what do I do next. There is something else sitting somewhere in here that is the executor that creates the waker and passes the waker out. But that is usually rather slim. So that is So for the example that I know best, that is the Riot OS example, that executor basically just packs up the current thread ID, because Riot is using threads, but just kind of they're sitting next to all this async stuff. It just packs up the thread ID and the and some chosen they call it a flag bit number, together with all the with the function table for the waker that is sitting somewhere in ROM. So it creates this struct of, I don't know, two word sizes or so, and and then just takes the big top level task and calls poll with the waker. So that is a very small thing sitting here, consuming maybe two or three words of RAM. But kind of the big parts that tend to explode are in here. So if you're keeping anything that any larger parts of memory across the wait points, that has kind of that very quickly makes these grow a lot.
That's the reason why the async runtime has to start first, initialize everything, and then everything else starts with tasks.
Yeah. Yeah, the async runtime has to start before the tasks can make progress. The tasks can be initialized, and they can be initialized statically. But in order for them to make progress, the execution needs to run. Okay. I think that's it. Thank you.